Okay. All right. So, before I get started, I want to tell you guys a story. Last Freak.
Deep throat the mic.
Okay. So, last PhreakNIC, I brought 2 college teams here from 2 different colleges, and we all played the CTF. Right? That's probably about 16 people, and we lost to 1 dude. And so, for the last 36 hours, I've been in mortal combat with this guy through the CTF, and I feel like I've been playing a Dark Souls boss, and for the last 36 hours, and now I have to give a talk, so it's like I'm putting my controller down at the last phase, and hoping that it goes well. So if I'm a little frazzled, I'm sorry, but we're just gonna get through it. So, Entropy. Reason why we're all here today. It's kind of the magical mystery of the universe. We're gonna talk about how you can apply it for pen testing, hacking, and doing cybersecurity stuff. So whenever I go to a talk, usually the first slide is who am I, and I really usually don't care who the speaker is. I just care whether or not I'm going to get anything through the talk. So this is my Corpo to Hacko speedometer, and I think my talk is going to land right like here. So we're not going to be writing the shell code or assembly. You should hopefully know what's going on. I'm still, lost on this one, not sure. Well, my goal is to make it so that this will improve how you hack. That's my goal for today. So we're not going to do anything super technical, but this is where we're at. So the idea. I'm not a physicist, but I was learning a lot of physics, and there's this really cool idea in physics that trying to understand the equations of motion, the first common sense thing you would try to do, is a really complicated and difficult process. But over time, physicists have learned how to use a different method, and instead of focusing on complicated bitwise operations and trying to figure out how each particle in a system moves, they'll instead just focus on the energy of a system, and that makes understanding the system much easier and much simpler. In cybersecurity, analyzing code is a really complicated, difficult, tricky process. Trying to understand little assembly for reverse engineering or stepping through a bunch of ancient C codes to try to figure out where the pointer is going, that's really hard. What's a lot easier is to just focus on entropy instead of code, and it'll do the same thing. You'll find vulnerabilities a lot easier if instead of trying to find bits and pieces of code to understand, you can just focus on the entropy instead. So, whenever you learn a math idea, you usually go through 3 distinct phases. The first one is, what is this? This is a bunch of crazy Greek symbols and I don't understand what's going on. The second stage is, okay, I don't know why they used all those Greek symbols to explain that idea. It seems pretty simple. What's the point? And then the third stage is, how have I lived without this? I was blind, now I see. So I want to take you all through these 3 stages in the talk. Hopefully after this talk you'll be driving in traffic and be like, entropy! So, entropy. What is entropy? Or, well, I told myself I would breathe and drink water at this part, so hold on. Okay. Entropy. So, WTF is entropy. You've probably heard the phrase, my only crime is curiosity. And really, if you think about it, curiosity is such a central cultural thing in the hacking community that it's almost like ubiquitous. If you think about it, it's just an appetite for information. That's all it really is. And so, the really quick way to see the link into entropy is that information is the opposite of entropy. Whenever you have a lot of entropy in a system, there's a lot you can learn about that system. There's a lot of information present in that system. So, entropy is a measure of average surprise for a data source. So if you understand exactly what state the system is in perfectly, there's no entropy there. You understand it like perfect, there's nothing there. If you're flipping a coin and you don't know where it's going to land, then in that case the entropy of that coin toss is 1. If you're flipping 2 coins, it's 2. So whenever you have some sort of data stream where you're learning information, that data stream or variable has entropy. So you have something that's like a coin toss, that's your stream, and then entropy is a numerical equation, so you can just get a number out of it. So any data stream you can think of, you can get this number value for it. So here's the math equation. I know you're all not math majors, but it's kind of pretty simple. Given a random variable, what you're doing is you're adding, you're just summing up the probabilities. That's all you're really doing. Except you're also multiplying it by the log of the probability. Add the negative at the front for a special reason. I don't know about you all, I'm not a math major, I'm a programmer, so there's Python. Python's much easier to understand. So literally just, if I give you a list of probabilities, for each probability of the probabilities, we're going to add up the probability times the logarithm of the probability. We just do that for all of them, and you get the entropy of the data stream. It's actually pretty simple. Okay. Hopefully you all will be able to see the font. Let's see.
Demo! Live demos.
Okay, that font is tiny, but we're going to do it.
Congratulations on using the correct window manager.
Thank you. I actually usually use evil, but I appreciate the compliment. Okay, yeah. We're not going to review the code. It's too tired.
Live code review.
Okay. So, I don't know if you can see that, but it says heads and tails, and it says 0.5 and 0.5. This is just a coin toss, so if you toss a coin, you have a 50% chance of head and a 50% chance of tails. Now, the program I run will calculate the entropy for it automatically, so let me run that real quick. I've never had to type backwards. This is weird. Cool, so if you can't see that, that just says that the entropy of one coin toss is 1. So next we're going to try a 10-sided dice. Cool, so this is a bit more of an interesting number. This one's 3.321 with some more at the end. The important thing is that there's more possibilities, there's more probabilities, so by adding them up, there's more information in the system. And that kind of intuitively makes sense. If you toss a coin, it can be in one of 2 states. If you throw a 10-sided dice, it can be in 10 states. There's more information there for you to get. Now I'm going to do 2 more examples. The first one is the alphabet, and that one is just if we talked like we were going to say the next letter randomly. I'm going to show that one, and then I'm going to show the one where the actual probability of the different letters that we use in the English language. Okay, so that's just saying for each of the different letters, if they all have the same probability and we didn't have things like words or structure or anything like that, then we would have an entropy of 4.7. Okay, cool. So here's something that's already kind of useful. If we take the actual alphabet, then we see the entropy has a value of 4.1. So,
Could you please cap those files to the screen?
yes.
All right, cap native letters, cap Pokemon, and cap alphabet.
Judgment.
I think you should bat. Oh, okay. There's your alphabet.
Okay, yeah, sorry for the font, but yeah, I mean, that shows that each of these different ones have different probabilities. So like the probability of T is 0.09 and the probability of Z is 0.0074. Cool.
Cool.
Okay, so there's a small difference here, but it's kind of a really interesting, incredible idea, and that is if you just have the naive letters, you have an entropy of 4.7. So there's more information in the system because there's the way the probabilities work out, that you're basically just looking at a random number source. But if you look at the actual alphabet, because it has structure, the entropy is lower. And so later on we're going to see that with different data streams, you can like kind of tell what it is just by looking at the entropy of what system you're dealing with. Okay, I think that's the end of part 1. So does anyone have any questions about the definition first before I move on? Because I'm going to start using it next. Cool. Part 2, but why? So, whenever you're programming something, I've been programming for like 10 years, and whenever you're programming something, what you're really trying to do in almost all the circumstances is create a new data stream with less entropy. And so, generally speaking, when someone says automated, what they mean is that the entropy of the data stream they've created is basically 0. So that's a really fancy mathematical nerd way of saying no surprises are going to happen because the system is going to handle every single probability there is. I think. Probably. This is where we sneak in. So there's kind of a hipster idea in AI. This was before modern reinforcement learning and all this crazy stuff they did, and that's where they just use entropy to try to make AIs and decision trees. So that's what we're going to look at next. So this is a decision tree for Morse code, and you can kind of see with the probability of the letters again. The most common letter is E, and so I don't want to have to press 15 buttons to say the most common letter. I just want to press 1. And so in this example, you can see they start off here, and then if they want to transmit the letter E, they just go dot. So they move over to dot. Then if they want to do T, they do dash. So they move over to dash. Because those are the most common letters, I have to press way less buttons. It's great. So if I want to say something really low probability, I have to do considerably more steps. So I have to do, for like Z, for instance, I have to go dash, dash, dot, dot. So because they've organized it in this setting, they have the most efficient way to communicate each individual letter. So here's kind of the classical case. Let's say we're trying to figure out what Pokemon we have and we don't have its name. So if I give you a database or a spreadsheet and I take a column out and I want you to predict that column with a decision tree and entropy, you can. So in this case, so for this case, the first starting out, we're at an entropy of 1.5. So we want to remove the most entropy that we can, and that's we can do that by sorting the table based on color. So if we see something that's blue, we'll just say it's squirrel, because that's all the data we have, so that's our best understanding. So if I give you some random thing like it's blue, you don't have to care about the weight, you just like squirrel. So if it's red though, there's another step, because we still have 2 possibilities. So we'll go over here, and you'll notice that the entropy of this table is higher than this table, because we've been removing information. So this one again, we just do the same step again. We try to figure out what split is going to reduce entropy the most, which is basically another way of saying what split is going to give us the most information gain, because information is the opposite of entropy. So the one more split, and then we have another data stream where the entropy is 0 because it's just one state, another data stream with the entropy is 0. Cool. So this is just another example of how decision trees work. Whenever you have an attribute with the highest information gain, you split up the data you have left, you do that again, and so you're basically splitting and you're cutting out parts of data because you've already considered them, the system has already handled them, you've already predicted them. So, hacking, as you all know, is about trying to find vulnerable inputs to systems. And so one way to do that is to look at all the complicated code of the system. Or on this slide, you just make it one word, system. Magic, who knows? The outputs you want really are, you don't care about, if you're hacking, you don't care about what it's supposed to do beyond that increasing your understanding of the system or the probabilities, I guess. What you want to find is this stuff. And so for all the given inputs, this is the stuff where we're going to put the magic in. So for all the working inputs, you want to try to query for the exploits. And so this is just a visual example of what we're going to be working on. Because you can see here, like the table, the columns, the spreadsheet, and all that, we had, we were trying to remove parts of the system. So, I mean, you kind of build a decision tree out here. But this is just kind of a visual representation. We're trying to find vulnerable inputs. So, in decision trees, you usually have a cutoff where you're just like, okay, I can't remove all the information from the system. I'm just gonna have a cutoff point. All right, any weird, unexpected, unintended behaviors aren't my problem. You know, it's just like, screw it, whatever. I'll just write an SQL query and put the string run on there, right? Not my problem. So there's a cutoff point, and that's usually where bugs happen, is after the cutoff point. And this is where, you know, the idea didn't come up during testing or anything like that. And so you don't need to understand all the behaviors of the system, you just need to understand what parts of the input for a data stream were likely to be overlooked. So the fundamental idea of a better way to find bugs is, instead of just like looking at a big pile of code, is to look at where the weird parts of the weird probabilities of inputs are. And so entropy leads to uncertainty, leads to things overlooked, and leads to bugs. Okay, cool. That's one part. The other thing I want to show you. This is the ent tool, and what it does is it measures the entropy of a file. And so you see if we curl the Wikipedia page for information theory, we get an entropy of 5.24, and then if we do completely random, we get 7.9. So the more random information is, this program will basically tell you how structured it is, even if it doesn't really understand what's going on. So this is something you can add to your methodology if you want to. So given an unknown file that the file utility doesn't work on, you can run ent on that file, and if the results are more than 7.5, it's probably unstructured, random, compressed, or malware, one of those. If it's not, then you can probably investigate this file just by opening up in like a hex editor or something, because you're probably going to see the structure. And how does it work? It finds the entropy per byte. So for each of the different possibilities of a bit, it'll find the entropy by adding it up. And so, yeah, basically finding the probability each bit is 1. We can do something similar. So what this basically does is it gets the probability of each byte you have in the file system. We're not going to do a code review. That's very messy batch, so we're just going to look at pretty pictures. So this is a bunch of text files I got off of textfiles.com. These, you can see here in ASCII, because you usually don't have a high bit set, you don't have to, you can kind of recognize the structure in the system in text, even though you don't really, if I just gave you a random blob of data and you showed me this graph, I could be like, it's probably English text. Here's code, here's C code from the Linux kernel. Now, hopefully you can kind of see the difference already. Like, you can already see the patterns kind of emerge here. Because code has more symbols in it, these lower bits have a higher probability of being activated, because those are usually symbols. So yeah, this looks like text. This looks like symbols. I don't actually have to read the file. I can just get the entropy of the file. Super cool. This is APL code. You can see the higher bits are set because APL uses weird special characters. And this one is completely random data, right? Each bit has the same probability of being on or off because it's completely random. So this is a cool tool you can put in your box, because if you have some big, weird, mysterious thing you've never seen before, just throw it in this and you'll be like, oh, okay, that looks like text, or that looks like code, or that's completely random malware. And if you're writing malware and you're like, hey, how can I make this less suspicious? Just put it in this, and if it looks like that, it's probably malware. And if it looks like this, it's totally normal text. What's up?
I'm not sure my head is processing your visual example as you intend, because I don't understand the relationship between the ordered example and the random example.
Cool. Hold on. Do you know what ASCII is? Okay.
Absolutely.
So the ASCII range usually letters like A through Z, right?
Yep.
Those, where do those occur? Where are they at? Usually, like, it's I'm not gonna remember. It's like 41 for A to.
Yeah, I follow that example.
Yeah.
Understood.
So because that's in a range,
Yes.
what you're probably not gonna have is you're probably not gonna use like the upper half. You know, you usually don't have the top bit set, which you can see here because it's text, right? So this line, that's the first bit, and you're not gonna set it because it's usually in text. This is usually the bits that show that it's text.
So I understand the value of an ASCII character. Your A is an example. So how are you going from that to graph example?
Hold on. Okay, we are gonna do a code review.
My favorite.
So,
It's a good scheme.
here's a file, right? We're counting it in. If you're one of those people who's just like, oh, you should do the pipe thing, whatever. I don't like you. So here's XXD. Here's XXD. That just gets the binary of the file, right? Here's us removing all the extra crap from XXD. More crap, more crap, more crap. Okay. So here we're cat the file. You can because we put it in a temporary file because we're going to go through it a couple times. This is called Choose. It's a really nice Rust program written by somebody. And what it does is it'll like select each column. So I'm doing a binary dump. I'm separating each bit out, each character out, so it's on its own column. And then I will select column 0, 1, 2, 3, 4, 5, 6, 7. You know, I will do each of them individually. So choose the byte, and then I will get the average value of it. So if it's a binary bit, the average value is the probability of it being 1. Does that make sense?
Yeah.
Cool. And then I've got this nice, cool thing I yoked from Stack Overflow, and that just shows the bar chart. So it goes up to the entropy, and then it fills in the rest. And then it removes our temporary file. Cool.
Understood.
Okay. Does that make sense? Does that make sense now? Cool. Okay. So those are the two big things I wanted to show you. The first one is decision trees, because once I understood them, I understood what I was doing in programming for the last 10 years. And the other one is entropy, because I've actually used that on engagements of like, I have this weird file, should I go down this rabbit hole? The entropy is 8. No, I'm not. Avoid that rabbit hole. Okay. Part 3. My eyes have been opened. Give me just a second. Okay. So this is a really cool math concept. The problem is that probability, just a word, is extremely complicated, and figuring it out in the real world is very difficult to do. And so different groups of people put different probabilities on events. This discrepancy is usually how hacking works, because you're like, they think you can't input some character or that character doesn't exist, and hackers like, yeah, no, it's a pretty easy possibility. So this is a number scale. At that end is low entropy, this end is high entropy. And if you think about it, an absolutely absurd number of cool things fit on this scale. So a really easy example is just learning. Like when you're unconscious incompetence, there's so much information and entropy and so much unhandled data you're getting, you don't even know what's going on. Then you can kind of start to slice it up. Then you can be like, oh, okay, I understand this now. I'm kind of automating, I'm kind of removing entropy, and then eventually it's just automated. Here's another one. Let's give you a task, and if it's too complicated for a machine to understand, then a human is probably gonna have to do it. And then there's some problems now where machine learning is taking over, where it's just like, okay, I can't make a bunch of if statements to tell if a picture is a bird. What I can do is machine learning, and then eventually get it down to the point where it's programming. So at each different stage, you kind of use a different technique. This one's kind of arty. It's just, you know, whenever something is, when you can't organize something down to like a hypothesis or a query or something like that, it's just kind of a noisy experience. That's when you make art, and whenever you can like put it down to like data and science, it's a science. Kind of, that's just my interpretation. Here's another one, boredom, flow, and anxiety. You know, whenever something is predictable, it's boring. Whenever something is way too complicated and too much noise, you have anxiety, right in the middle of flow. Cool, now we get to the part where we can actually use this. So, generally speaking, whenever I'm hacking something, it usually can start with like an IP address, and then I will try to find the most common ports, and then I will go down to the most chaotic, least likely ones. If I've got some sort of like field that I'm trying to inject something into. The first thing I'm going to try, like it's a password field, right? I'm going to be like the actual password all the way over here, if I just knew it. If I didn't just know it, then I'll look up like the version number of that system and see, okay, did someone else already figure this out? If that doesn't work, then I'll be like, okay, common vulnerability strings, SQL injection, command injection, whatever. This is the secret magical hacking sauce. This is where people make their money because it's not really structured, no one really knows what's going on. At this end, this is where I'm just like, screw it, I'm just gonna get a bunch of text fields off of payloads, all the things on GitHub, and just throw it and hope I remember to turn my VPN on. This one is just complete fuzzing. This one's just like you cat the random number generator into the system and hope something breaks, but you don't really have any understanding or knowledge of the system. Now, for each of these different parts, you can be like, they keep showing up in different fields in hacking. Like, you can apply this idea of going from low entropy methods to high entropy methods in any data stream you see, basically. Yeah, so for instance, like high entropy methods, lots of sample space, lots of brute force. Low entropy methods require lots of previous knowledge, but they have small sample spaces. And so if you're reading a write-up and you're like, oh, this is so cool, but only applies in this field, if you can learn how to abstract the idea behind the methodology, you can start to apply it to a different context. So if you like, doing an SQL injection, and you're like, oh, okay, if I break this open with a quotation mark, and then I can inject into it, that's cool. Oh, hey, I can apply that same idea to command injection. So really, if you know how to abstract things in cybersecurity, there's not a lot of tricks. There's just tricks applied to different contexts, if that makes sense. Also, hacking tends to be recursive. Usually I will hack something and then I'll get a list of 10 more things to hack. I've got an IP address. I port scan it. I have now a list of ports to try to hack. I go to those ports. I see a web page. I see a bunch of fields to try to hack. It's kind of recursive. So combining these ideas together, what we get is our meta methodology, where for each data stream we have, we try to get more data streams. And we try to get more data streams by using each methodology we know in that context from low to high entropy. So there's kind of like a hacker smell, almost, literally and metaphorically. So what you can do is, like, if you have, that joke just completely ran my, hold on. Right, so usually whenever you have a list of things that you're trying to hack, like a port, like if you give an experienced pen tester a list of ports, he'll know which one to go to first. So like, if it's a file system, he'll probably go to that one first. If it's port 80, he's gonna try that one next. And then if it's some weird, strange port he's never seen before, you might try that last. And so your ability to sort things in cybersecurity is a critical fundamental skill, regardless of what context you're in, red team or blue team. And so by being able to sort things effectively, by looking at the entropy of a data stream and deciding based on that, whichever is the lowest one I'll try first, it's a really valuable way of getting into it gives you that instinct that's really hard to define. I think entropy is a fundamental part of it. That's not the only part, but it's a fundamental part, and once you understand it, it makes it a lot easier to see different ways of doing things. Cool, so now with this idea, the idea that we can steal ideas from other fields, where should we look? I have great news. I'm not that clever. I didn't come up with this. This is just math. This is actual math. It's not just doing boring things with numbers. You can do lots of crazy, awesome things. We've been stealing ideas and putting them in math for thousands of years. So if you learn math, you learn a lot of really cool methodologies. All right, now for my self-help guru section. In life, you can kind of view all your senses together as a data stream. So people have a natural appetite for entropy in their life, So variety is the spice of life is a really good example of that, and you can see, if you live the same day over and over again, it's very predictable. You kind of remove the entropy from your life, and you can feel it. So if you understand this, it's almost like understanding calories in food. You can start kind of counting them and trying to live a little bit better. And then lastly, when I was procrastinating making these slides, I was watching a YouTube video, and I saw this comment, and I thought it was super cool. So he sees everything, knows everything, and can do anything and everything at any point in time. And at that point, what is the point of life? Uncertainty and the unknown is simultaneously the biggest fear of mankind and also its greatest blessing, which is such a beautiful idea. So that's my talk. I am very under on time. I can keep rambling if you all would like. I see a couple of minutes.
Go beat the Dark Souls ball.
Also, here's Steve.